The conservation of momentum for a system of particles existing within a certain inertial frame is very useful because it allows us to solve for the masses, for the velocities of particles if masses are known before and after a collision. So if we knew all the system of velocities and masses before a collision has occurred, then in a rather easy way using the conservation of momentum, we can solve for the velocities after the collision has occurred. However, with one equation like the conservation of momentum and two unknowns, those two velocities v1 prime and v2 prime, after the collision has occurred, we don't have quite enough information to solve for everything we need to know. Therefore, we need another equation that relates the v1 prime and v2 prime, the two velocities after the collision, to the momenta before the collision. And we will use two idealizations or approximations to get that extra equation. In one extreme case, we'll consider an ultra-inelastic collision, one which you can imagine is like two big balls of Play-Doh being thrown at one another, and they stick together. That would be referred to as inelastic. They don't bounce at all. They just stick together. In this case, the two velocities, whatever they are, of the two objects after the collision will be the same. We can write v1 prime equals v2 prime. That provides another constraint, which, along with the conservation of momentum equation at the top here, allows us to solve for the velocities of the particles after the collision. And we may write m1v1 plus m2v2 is equal to the sum of the masses times this single velocity v prime. If all the masses and the initial velocities are known, we can solve for this final velocity v prime. Another extreme case that we can solve is, again, something of an idealization because nothing in nature is perfect, but one in which the two objects are elastic and they literally bounce off of one another. In more precise terms, we write that mechanical energy is conserved in such a reaction, and so the initial kinetic energies of the two objects colliding summed together equal the mechanical kinetic energy of the system, and whatever the velocities are at the end, we'll say that the total kinetic energy of the system is the same as it was at the beginning, and therefore we can write 1/2 mv squared for the two particles at the beginning equals 1/2 mv squared for the two particles at the end. This also gives us a second equation relating the final velocities to the initial velocities, which, along with the conservation momentum equation at the top here, can be solved for two equations and two unknowns. There's a lot of algebra necessary to complete this solution, but I'll simply quote here the results. After the collision, v1 prime equals the ratio of m1 minus m2 over m1 plus m2 times v1 plus the ratio 2m2 over m1 plus m2 v2. The second velocity, v2 prime, looks in algebraic form exactly like the first one, except the roles of mass 1 and mass 2 reverse. So it becomes 2m1 over the sum times v1 times, or plus the difference in masses over the sum times v2. Those are rather long, complicated equations, and it's helpful at this stage to get some practice thinking about what they mean. So let's look at some elastic collisions. Because the formulae for these velocities after elastic collisions are kind of complicated, we'll take some special cases in order to make some sense of what the formulae mean. Let's try, for example, with the case of a projectile particle hitting an initially stationary target. By stationary, we mean that its velocity is initially 0. So let's say that that's particle number 2, that it will eventually have v2 is 0. The picture of this would be then that mass 1 is moving along at some speed v1 and heading for mass number 2. Looking back at our equations, they simplify in this case to v1 prime is the difference in masses over the sum times v1, and v2 prime is 2m1 over the sum times v1. What does this mean? It means that both objects will be moving with some speed, potentially, after the collision, but there are some rather extreme cases. And again, it makes sense to help our intuition to look at the extreme cases. One extreme case comes when mass number 1 is extremely large compared to mass number 2. This is not unlike a bowling ball about to run into a little ping pong ball. Intuitively, we would imagine the bowling ball just keeps on going and the ping pong ball is kicked forward. If we look at the two expressions here at the top of the page for v1 prime and v2 prime and imagine what happens when m1 is very, very large compared to m2, then we see that for v1 prime, I essentially have a ratio of m1 in the numerator over m1 in the denominator. In other words, I can ignore or set to 0 m2. And since this ratio inside the parenthesis is 1, I have that v1 prime is essentially equal to v1. If I look at v2 prime, I have 2m1 in the numerator and essentially m1 in the denominator when I set m2 to be approximately 0. And I find that v2 prime equals 2v1. In other words, the ping pong ball does indeed get launched forward, and it gets launched forward with twice the speed that the bowling ball is coming at it. So imagine a Mack truck hitting a small VW Beetle, which was parked right in front of an intersection. The VW Beetle will keep on going, but much faster. Let's imagine the opposite case where m1 is much less than m2. Since m2 is the one that's initially stationary, this is like trying to throw a ping pong ball at a large bowling ball. And what happens when m1 is essentially 0? Well, in the equation for v1 prime, I have 0 minus m2 over 0 plus m2. And this thing inside the parenthesis is essentially minus 1. And so I have v1 prime equals minus v1. v2 prime will essentially equal 0 because m1 in the numerator is 0 and it's divided by the sum. And this is not unlike our intuition. If we threw a ping pong ball at a very large bowling ball, then it's unlikely that the bowling ball would move. In other words, its velocity at the end would be 0, and the ping pong ball would just come bouncing right back at us. Or imagine we threw a ping pong ball or a bouncy rubber ball down at the earth. The earth isn't likely to move all that much, and the rubber ball will come right back at us. The last extreme case to think about is when the two masses are identical in mass. m1 equals m2. This is like taking a tennis ball and throwing it at another tennis ball. Here, something unusual occurs. When m1 equals m2, then in the first expression here, the difference equals 0 divided by the sum, and v1 prime will just equal 0. And v2 prime will equal 2 times the mass divided by 2 of the equal masses. So this ratio will equal 1. And v2 prime just equals the initial speed of the projectile. In this case, we have something not unlike the kind of toys that you see on office desks where you have little bouncy balls that hang from strings, and when one hits the other, it comes to a dead stop, and the second one, the initially stationary one, moves forward with the same speed as the original one was moving.